Now let's take a look at these. So maybe some of you have seen this addition to yesterday's notes. If not, maybe you could take a look at this now. We'll begin with a couple of examples. So has anyone tried a for this this example? Is x e to the xy differentiable at 1, 0? You know, what should we check to make sure that a function is differentiable or not at a point? Right, you want to check if partials are continuous, right? So what are the partials in this case? What's the x partial and what's the y partial? So your function is x e to the xy. So what's partial x of this? The partial x of this, we'll have to use the product rule. So partial x could hit the first factor of x here and leave you with an e to the xy. And then it could hit the second factor, which gets you an x, or it gets you an y out front. So this is xy, e to the xy. And for partial y of this, you're going to end up with, well, you want to differentiate in y. So it hits just the e to the xy part. And you're going to get an x squared e to the xy. All right, so are these continuous functions? Right, so these are continuous. In fact, it's continuous everywhere on R2, which is more than what you need, but it's, certainly it's differentiable at 1, 0. So it's differentiable at 1, 0 in particular. So to be differentiable at a specific point, you just need continuity at that point. All right, so it doesn't mean that the partial derivatives exist at that point. You need the fact that the partial derivatives exist, in this case at 1, 0, and also the partials exist nearby, in the sense that you could evaluate the partials and prove that the partials themselves are continuous at that point. All right, you could see an example of this in the release practice test. There's one question on that. Okay, so how do I find the approximate value for 1.1 and minus 0.1? What's a reasonable base point for my approximation here? Right, so I could try 1, 0. So for the approximation, we could linearize near the point 1, 0. Right, so what we need, well, we need the following inputs. At 1, 0, we need f at 1, 0. We need partial x of f at 1, 0. We need partial y of f at 1, 0. Does someone want to volunteer these quantities? So let's say at 1, 0, we have y is 0, so this is just 1, and we have x e to the xy is 1, right? So in the partials, you do the same process here. You could plug in at 1, 0 into the relevant formulas here. So you get 1 for partial x, and then you get another 1 for partial y, right? So this tells you that the linearization near 1, 0 is going to be f at 1, 0, so that's 1, plus partial x of f, which is 1 times x minus your base point, which is 1, plus 1 y minus your base point, which is 0 in y. And so this is 1 plus x minus 1 plus y. And what is this? This is just x plus y. All right, so what is the linearization at the particular point that we want? So we've linearized at 1, 0, and we want to plug in 1.1 minus 0.1. So we have the following. F at 1.1 minus 0.1 is approximately equal to its linearization because it's differentiable in particular. And so we plug this into our formula, and this is just going to give us 1. So here's our formula for our linearization that we just used. Right, here's our formula for L. Here's L. We plug in 1.1 minus 0.1. All right, so what is the equation of the tangent plane to the graph z is equal to f of xy here? So let's do, the tangent plane is given to you by the linearization, right? Okay, so we have a candidate here already given in chat. Let's see how we get that. So we want, the tangent plane is, you want the linearization at 1, 0, which you just had. So you want to take the plane given by z is equal to your linearization. So this is equal to, z is equal to your linearization, which is x plus y at that point. And you could rearrange this if you want to standard form, and you get this. So remember, if you're rusty on this, look at yesterday's lecture notes. The linearization for differentiable functions, that's functions with continuous partial derivatives. There are two interpretations. One, right? The first one is your linearization gets you something that's a good approximation to your actual function, your point, right? That's the interpretation that we use here in your approximation part. The other interpretation is geometric. If you take the plane given by your linearization, assuming you're differentiable at the point, then the plane equation given to you by z is equal to your linearization, that gives you a plane that is tangent to that point, where the point is your graph z is equal to f of xy. All right, so let's look at example B now. So what are the partials at 0 here? Okay, so let me address the question. 1, 0, 1 is precisely what this point is, right? We've taken our linearization at the point x is equal to 1, y is equal to 0, right? That's what we've done here already. We've linearized near 1, 0. At x equals y, so at x, y equals 1, 0, we're at z is equal to 1, right? Just plug that in here. You're at z equals 1. So this is precisely the point given to me by the linearization, the graph of the linearization at that point. All right, so I've linearized here, which means that the graph of this gets me exactly the tangent plane at this point. Okay, so moving on for B, if I'm considering this function here, what are the partials, partial x and partial y at 0? So what's the strategy? Let's say partial x of f. How might I have a piecewise defined function here? How do I evaluate its partial x? Right, so for partial x of f at 0, 0, if it exists, this should be given to me by the limit as h goes to 0 of f of h 0 minus f at 0, 0 over h. Right, that's a difference quotient definition of a limit, right? We're back to basics because we don't have any of the usual tricks that we could apply, because this is not a usual function that's nice and differentiable, obviously, right? So we have to resort to our basics definition. And sorry, let me just add a page. So what is this? Well, f at h0, right? This is, I plug in, when x is h and y is 0, I certainly go here because x, y is not 0, 0. So I have this here. So this is x is equal to h, y is equal to 0 over h squared plus 0 squared minus f at 0, 0. I plug in the rule here, right? It's 0 all over h. Well, I mean, here it's h times 0 in the numerator. This whole thing disappears. So this is just the limit as h goes to 0 of 0, which is 0. And partial y 0, 0 is also 0 by the similar calculation, right? So we've done, back when we were discussing how to take limits last week, we've done essentially the same thing, right? Back then, we just took the limit along different paths, if you will, of this function at 0, 0, and we found this. Okay, so suppose you have a linearization formula. Let's say L of xy is what would be a linearization at the point 0, 0. All right, supposing you're if you just apply the formula that we used here blindly. And the question is, does L xy approximate this well at 0, 0? So what do you need to check to see if the linearization approximates f well at the point 0, 0? Right, so remember, this is exactly the definition of what it means to be differentiable at 0, 0. So, you could say L of xy approximates f well if it's differentiable, all right? So you got to check if it's differentiable at all, which means you got to check if it has continuous partials. So L approximates f well near 0, 0 is the same thing as f is differentiable at 0, 0, which means that the same thing as partial xf, partial yf are continuous. I mean, they exist and are continuous at 0, 0. So this is what you need to check. So how do I check this? I should evaluate my partials away from 0, 0 first, right? So partial x of f, so away from 0, 0, I have the following. Partial x of f is going to be equal to this function here, right? We're away from 0, 0, so you could use your usual differentiation rules, right? So I could use the quotient rule, for example. So this is partial x of xy over x squared plus y squared. And the numerator is the denominator times derivative of the upper minus the upper over the derivative of the lower, which is 2x. And so we could simplify this. This is an x squared y here. This is a 2x squared y. So you get a y cubed minus x squared y up top. What you might do is you look at this now and you say, does this converge to 0 at 0, 0? Right? Remember, partial x of f does exist at 0, 0. We just checked it above. and it's equal to 0. Now, you need to check if this is continuous, which means that when you're away from 0, you're here, and as you approach 0, 0, you want this to converge to 0. Any ideas of whether this does or not? Right, so we're looking at the limit at 0, 0. So let's pretend, let's substitute in polar coordinates to see if we could get an intuition, right? So what power of r appears down here in the denominator? Right, it's r to the fourth. Right? This is r squared to the, to square it again. That's r to the fourth here. What's up top here? Right. So how does r cubed over r to the fourth behave as r goes to 0? Does it go to 0? Does it go to infinity? Is it something else? Right. So note that this behaves like some r to the third over r to the fourth, which seems to not converge as r goes to 0. So, okay, well, can we make this concrete? Well, it seems like now this does not seem like the limit as xy goes to 0, 0, partial x of f is equal to 0, right? So partial x of f is not continuous at 0, 0. So L of xy does not approximate f of xy well near 0, 0. All right. Now, how could we see this concretely? The formula for partial L of xy is equal to, at 0, 0 is f at 0, 0 plus the partials, right? Right now, f at 0, 0, we've, by the definition of our function here, f at 0, 0, 0, right? We've evaluated partial x, partial y at 0, 0. They're also equal to 0. So what we have is, this is 0. However, let's say along the line x is equal to y, f at, when y is equal to x, this is equal to x squared plus, well, it's xy, right? So that's x squared over x squared plus y squared, right? So this is 1 over 2. And so what we have here is this function is not even continuous at 0, 0, right? This is not equal to f at 0, 0, which is equal to 0. So your linearization here, if you just blindly apply this linearization formula for this particular f, right? Its partials exist, they're equal to 0. Your linearization comes out to be 0. So theoretically, you want, okay, well, for x and y near 0, 0, in essence, especially at the point 0, 0, I want L to be close to what f is. However, if you approach along the line x equals y, no matter how close you are to 0, 0 along the line x equals y, this is always going to be stuck at 1/2. All right, your value of your function along this line is always 1/2, which is definitely not close to 0, right? You can't make 1/2 approach 0 along this line. And so near the point 0, 0, this is not a good approximation of f, because f is identically 1/2 along your diagonal lines. Yes, if you suspect it's not continuous, you could in fact jump to this directly. All right. So if you recognize, I mean, you have the notes for the exam, right? So if you recognize something like this, which we've done before, then you could say, okay, your argument could specifically say, okay, my linearization formula is this. It's always 0. However, along this substitution, I'm always at 1/2. And so this is definitely not a good approximation near the origin. Okay, I just wanted to show concretely, if you had something more complicated, you have to justify by saying partial x of f is not continuous. But this is the concrete version of how you could see in this particular example why, how this formula could still exist, but be absolutely horrible at approximating your function when it's not differentiable. Okay, let's move on to a slightly different topic. So suppose I have a function that's differentiable. All right, it could be 2 variables, 3 variables, any number of variables. And furthermore, each of these variables are, parameterized or maybe functions themselves of other variables. So in the classic case, pretend f is, the temperature of a room at some point. And let's say x, y, and z are give the trajectory of some fly that's flying around the room. So this is, for example, a parameterized curve, right? Then maybe if you're the fly, then you want to say, okay, I want to know at time t along my path, how fast is the temperature changing? And if you're a really smart fly who knows calculus, then you do this, right? You do df dt is what you want to calculate, where f of t is just you plug in your parameterization to x, y, and z, So f is now a function of t. And so how this works is it's essentially just like how the one variable chain rule works, right? You do, the way you write this, you could pretend you're canceling out fractions, right? df dt, you could go through how x depends on t. So this is partial f, how it depends on x, and then how x depends on t, right? Informally, dx cancels, you get df dt. However, unlike the one variable case, your function here can depend on t through the other number of variables that depend on t. So the other option is you could go through y and do the same thing. And you also go through z and do the same thing. So altogether, this is a chain rule in multivariable when all the parameters depend on t. So this is, pretty, hopefully not too bad to pick up. Now there's a more general chain rule, and that's the case where let's for simplicity's sake, let's keep the same function of three variables, and then x, y, and z, instead of being functions of the same variable, just one, t, you could say x is dependent on variables u, v, and w. Let's say y is dependent on just u and v, and z is dependent on u and w and s. All right, where s is completely does not appear in x or y. All right, so you might wonder, okay, so what's the example of this? Well, it turns out in a lot of these situations, for example, economic models, if you've taken some intro econ or economic models in general, you have oftentimes very complicated modeling functions. All right, so these are functions, maybe it's like labor output or something, but then your inputs include a lot of, maybe x is the cost of labor at maybe one factory, y is the cost of some other thing, and z is maybe the cost of rentals. All right, but maybe each of these parameters themselves are also dependent on different or the same parameters. For example, maybe the cost of labor at factory A is dependent on u, and v, and w, which have to do with interest rates, maybe of the particular province or state that the factory A is located in. Maybe y is at factory B, it's in a different location, then y is also dependent on interest rates. And maybe, there's an extra tax or something at the separate location. So y depends on a few other variables and so forth. In essence, this is not just a made up math thing, right? It's like you have an actual model with inputs, and these inputs themselves could depend on several variables. And you oftentimes, in econ, you hear about things like price elasticity of demand and such. To figure those things out, you need to take partials with respect to various different variables here. So this is very complicated to see, right, in general. So the question is, how could you take derivatives with these differing dependencies, right? If x and y and z depend on these parameters I've written here, then overall f, when you plug these in, it depends on u, v, w, and s. It's a 4-variable function now, right, in terms of all these inputs. So it's actually not too bad once you look at it the right way, which is a tree diagram. What you have here is labeling the dependencies. At the top node, I have my function f. It immediately depends on x, y, and z, right? That's how f is presented. So I put x, y, and z here on the first level, right? And I connect these with gray. Now, on the subsequent level, I also have further dependencies. X depends on u, v, and w. So I put u, v, w here. Y depends on u and v. Z depends on u, w, and s. And now I just need to select down the correct paths to choose my partials. So suppose I want to choose the partial of f with respect to u. Now u appears here, here, and here. And so I need to retrace the paths that connect u, all appearances of u, back to my function f. The first one is here. U is connected to x, and x is connected to f. So here, I have a term that is partial f, partial x, and partial x, partial u. Now over here, I have, so that takes care of the dependence of u via x, right? This first term here. I have another appearance of u here that depends on y, and which depends on f. Or sorry, f depends on y, which depends on u. So I have another chain rule application via y over here. And for u appearing here, I have an application via z here. So I have a question in chat is, so it's modeling changes in a function when something very basic changes down the order. Well, kind of, yeah. It's like, if you have like some maybe some model for profit or something and of your company, and you had all these inputs, and maybe interest rate is at these different factories, then you want to see how maybe a change in interest rate affects things. So that's where this comes in. So this takes care of the example for you. Let's suppose you want just to do the derivative in S. So you look at S here. Well, S actually doesn't appear in X or Y. It only depends here. So there's only one path to get from F to S. That's via Z. So the chain rule for S really just involves this term here via Z. And you could do the same trick for the other dependencies. Let's do an example, which I had added yesterday. So we have the following. All right, we have a function U. Let's draw the tree diagram for this. So I have U up top. And what goes on the second layer? How many branches of the tree do I have, and what do I write in this case? Right, there are two branches that come out, and it's X and Y, right? Because here, this is my top level function, and it has inputs X and Y. What goes underneath X? How many nodes does X have? Right, so X has two nodes, S and T, right? Because here, X is doing on S and T, and the same thing for Y, right? So in this case, it's a pretty symmetrical looking thing. So does someone want to give me the chain rule for partial S of U? So du ds, how do I evaluate this using the chain rule? So maybe in symbols first, to get to S, I need to go from U to X to S and U to Y to S. So this is partial U, partial X, partial X, partial S, plus partial U, partial Y, partial S. All right. And maybe let's just record down what the other one is as well. So partial T, partial U, or partial T of U is going to be this. Right, so let's just collect the terms, all right? So maybe if we evaluate all these partials separately, we could just plug things in. So partial X of U, that's going to be e to the X sine Y. Partial Y of U is going to be equal to e to the X cosine Y. And then we have the various partials we need in X and Y, right? So we have partial S of X is equal to T squared. Partial T of X is equal to 2TS. We have partial S of Y is equal to S squared T. And partial, I lost track, right? Partial T of Y, that's the remaining one, is equal to S squared. Sorry, I screwed this one up. Partial S of Y is 2ST. And now let's see this at ST is equal to 1, 2. Let's evaluate this. This is at ST is equal to 1, 2. What are the values of X and Y? So you're at S equals 1, T is equal to 2. So what are X and Y? So I could plug this in here. Right, so X is equal to 4. Maybe I'll write this down here. XY is equal to 4 and 2. And so this is equal to e to the 4 sine 2. Then you have e to the 4 cosine 2. Then here, you already have expressions in T and S, so you don't need to plug in XY, you plug in S and T. This is going to be at 4, right, equal to 4. T of X, so that's 2TS. That's going to be equal to 4 as well. All right, so now you can just plug things in, right? So at ST is equal to 1, 2. This is, so partial U of X is here. Partial X of S is here. So it's 4 times e to the 4 sine 2 plus partial Y. So this is e to the 4 cos 2 times 4, right? And similarly, you have something in partial T of U. And so partial X of U is the same as well. You have an e to the 4 sine 2 here, but you got to multiply that by partial T of X, which is 4. And then you have e to the 4 cosine 2. You got to multiply that by partial T of Y, which is 1. All right, so now the question is, how do I get partial S of partial T? So let's take a look at this. Right, this is taking the derivative in S on the derivative of U in T. This is dds of the following. The derivative in T is going to be this here. Now, you do not plug in this, right? This is the derivative of U evaluated at a particular point already. Right, if you take a derivative of this is constant, this is 0, right? That's not, you need the general derivative in T here. So you read off what this is. So partial x of u, this is e to the x sine y. This term here is this, e to the x sine y. Partial x of t is going to be 2ts. Similarly, you have the second term. Partial u of y is e to the x cos y, and partial t of y is s squared. So what do you get here? Well, this is dds of 2ts e to the x sine y plus dds of s squared e to the x cosine y. Now let's take a look at this term here. So we could apply the product rule here. 2ts is a function of s, right, clearly. E to the x sine y doesn't look like a function of s, but remember, x and y depend on s and t, right? X and y depend as such on s and t. So these are actually, you don't see it, but x and y depend on t and s. So let's hit this part of the product first. And you get a 2t e to the x sine y plus 2ts times partial s of e to the x sine y. What do I do to evaluate this? Well, we could substitute. I mean, the idea here is this is chain rule, right? This is chain rule again and s for this function e to the x sine y, but fortunately we've already done this, right? E to the x sine y is u, so we could substitute, as in chat, this, right? This term here is exactly this. And now at this point, we already evaluate this as e to the 4 sine 2. So this portion here is evaluated above already. So what do I get? I plug in, right, at st is equal to 1, 2 again. This is 4 e to the, so x and y are going to be equal to 4 and 2 again. So it's e to the 4 sine 2 plus 2ts is going to be 4 again. 4 times e, this derivative at the point 1, 2, we could read off here. This is e to the 4 sine 2 again. This is 8 e to the 4 sine 2. And this, just in the interest of time, I think I'll leave this as an exercise for you guys, right? So you do the same procedure here, and you plug in what you know, and there you go. Any questions here? How do we get e to the 4 sine 2? Well, which one? I mean, there's a lot. So you're taking, first of all, the question asks at st equals 1, 2. So at st equals 1, 2, you plug in what x and y have to be, and you get x is equal to 4, y is equal to 2. And so e to the 4 sine 2, that just appears when you plug in the points here, right, when everything appears. So I don't know why e to the 4 sine 2. Well, because when you plug in e to the x, this is 4, this is 2, this is e to the 4 sine 2. Over here, why is this e to the 4 sine 2? Well, because I read it off here. Partial s of this function I've already evaluated, and at this particular point, I know it's e to the 4 sine 2. It's not implicit differentiation. Here, maybe because gray bothers people. Here's the gray, all right? So here's a gray. But this has nothing to do with implicit differentiation yet. We haven't gotten there. Right, to recap, how did you take the second derivative? Well, you just, use the second derivative. You found the first derivative, which is by this formula. It's kind of annoying because x and y depend on t and s. You just don't see it explicitly. But I'm pointing out that you could still apply the usual product rule in s. So first we split up the sum to make it easier. For this first part, you apply s to this first part of the product to get this. All right, remember x and y still depend on s and t. I just didn't write it out. Over here, you keep this first factor in place, right? You keep this first factor in place and you hit dds on e to the x sine y, right? Because x and y depend on s, dependent here, explicitly. And you need to use chain rule here. Fortunately, we don't need to use chain rule from scratch because we already evaluate the very same thing here, right? And because we evaluate the very same thing here, we just read off what we already calculated and we're able to substitute this part in. All right, in general, this is not true, right? In general, for this particular function is true. In general, you have to see, what comes out and what happens there. And the first line of purple is literally just the product rule in S. All right, so that's the example in the chain rule. So the remaining part is implicit differentiation. What is implicit differentiation? Well, first, let's recall what it means for a function to be implicitly defined. All right. So here's my function, my example function, x squared plus y squared. All right, it's a function of 2 variables in 2 dimensions. Let's take, you could evaluate the partials relatively easily, right? These are the partials. And you see the partials are very nice. They're continuous, right? It's 2x and 2y. They're continuous functions in 2 variables. Nothing weird happening. Now, let me with this function, I could look at the set of solutions f of x, y is equal to 1 or 2 or any constant, say, right? So what is this? Well, in this case, it's x squared plus y squared equals 1. And the solution, as we know, it's a circle, right? The circle gives you all the possible solutions in R2 to this equation. But we also know the circle could be described by moving these things around, right? If I have x squared plus y squared equals 1, I could just, let's say, put x squared on this side and take the square root. I could choose a positive square root for this and negative square root for this. So in other words, I could always describe y as a function of x so long as I'm not at these 2 points. At these 2 points, I cannot write, if I'm below these 2 points, I can no longer write, I don't have a function that describes my point as a graph in terms of x. In particular, at these 2 points, y outside of these 2 points, you could always define y as a function of x. That means via this formula here, x squared plus y squared is equal to 1. This implicitly defines a function y in terms of x. All right, so that's what it means for something to be implicitly defined. And furthermore, maybe you recall in one variable as well, instead of doing dy dx of this function here, right, this requires, differentiating with a square root here and using the chain rule, which is a bit annoying. You could actually just differentiate this equation directly, right? So suppose if y were defined as a function of x, which it is here, then certainly, these points here satisfy the equation f of x, y is equal to 1. So you have this here, right? Y is now a function of x. It's defined implicitly, but nonetheless, it satisfies f of x, y of x is equal to 1. Now I could differentiate both sides of this. Right on the left-hand side, I take d dx of this. I haven't evaluated yet, but I'm hitting this with a derivative. On the right-hand side, right, because this is always equal to 1, I hit the right-hand side with a derivative in x, it doesn't change. This is derivative of a constant, it's 0. Now I could apply the chain rule to this part here. What the chain rule says is I could differentiate f in terms of x. Now what's the dependency here? My dependency here is f. It depends on x and y. But y here is defined implicitly in terms of x. So this y also depends on x here. So there's another node here with a branch of the tree. So when I differentiate in x, I follow here. So this is the partial x of f. And there's another way of reaching x, which is through y. That's partial y of f times partial x y. That's here. So what do I have here? I have this formula. Dy over dx is equal to minus partial x of f over partial y of f, right? Just by moving this algebraically around. And this works whenever this is defined, right? Partial y of f cannot be 0 because you can't divide by 0. But, this formula holds true wherever partial y of f does not vanish. All right, so what's the point of this? Well, the point of this is this function here, x squared plus y squared, is very easy to differentiate in terms of x and y, they're partials, right? And what you're saying here with implicit differentiation is wherever partial y of f doesn't disappear, if you have y as a function of x, that is, you write a portion of your circle as a graph, y is in terms of x. You don't have to differentiate this in terms of x directly. You could read off what the differential is just by relating the partial derivatives. All right, so that's what I've done here. So we're a bit short on time, but I hope this computation is clear. I did the exact same procedure as I outlined here abstractly. This is your f of x, x squared plus y squared. On the unit circles, x squared plus y squared equals 1. Take derivatives both sides, and you get, by implicit differentiation, 2x, because that's partial x of x squared, and then partial x of y squared is this, right? You have 2y times dy dx by the chain rule. And at this particular point, things are nice. Your denominator doesn't vanish, and you have your derivative dy dx in this case. So maybe now let's take a look at, for any number of variables, you could play the same game. By the way, one exercise you should do is on this point here, right, on the right hemisphere, or the semicircle, sorry, the right semicircle, could also be parameterized x in terms of y, right? I could, for every y here, I could tell you what this is just by taking, let's say x is equal to the square root of 1 minus y squared. That's x as a function of y. And you could do the same thing here, but in this case, you'd have f of x of y and y here. So you could evaluate dx dy just by doing a variant of this, right? You could do ddy here on both sides and see what you get. Okay, so there's a question, how did I get the value of y to evaluate? Well, I know at x equals 0, or sorry, x equals 1 over root 2, I need 1 over root 2 squared plus y squared is equal to 1. So there's two possibilities, right? Y could be equal to plus or minus 1 over root 2. But here's my function. My function is d dx of 1 minus x squared. So my 1 minus x squared at 1 over root 2, that tells me y is equal to the positive square root of 1 minus x squared. That's 1 minus 1/2, so it's positive square root of 1 over 1/2, so that's y is equal to plus 1 over root 2. Maybe I should specify here. In this case, right, this is y of x is equal to the positive square root of 1 minus x squared. So at x is equal to 1 over root 2, y is equal to plus 1 over root 2. No, this is not based on f of x, y equals 0. We're not doing f of x, y equals 1. That defines a circle. So here is the dependency on y. You read off y, y defined implicitly in this sense, it has this. So in general, you could have z of x, y is defined implicitly by in terms of this. Let's say 3 variables. So f is a function of x, y, and z, and you have some constant c here. You could play the same game. You could also do the same game for x as a function of y, z, or y as a function of x and y. So for example, partial x of f, you can evaluate this. If you consider z as a function of x and y, then you do the chain rule. The same procedure as before. Partial f depends on x via x itself and also via z. There's no dependency of y on x. So the right-hand side derivative is 0 because it's a constant. You write this out and you see that partial z of x is equal to this quantity here. So if z is defined implicitly by f by this function here, just like how y is equal to 1 minus x squared is defined implicitly or satisfies the function x squared plus y squared is equal to 1, right? This squared is 1 minus x squared, so added to x squared, this is equal to 1. When that is satisfied, then you could, instead of doing dy dx directly here, or partial z partial x directly here, you could instead take partials of this function here and plug in the relevant values. So does the choice of your constant matter? I mean, as long as it's a constant, right? It's so long as you could verify that the function that you're actually trying to differentiate, in this case dy dx, this always satisfies x squared plus y squared equals 1. For example, if I change this to like x here instead of 1, the function x squared plus y squared, when I plug in this y, does not satisfy x squared plus y squared equals 1. So because that's not a constant, you can't differentiate x squared plus y squared to get anything related to the derivative of this, right? The choice of constant doesn't matter. You don't really, in a sense, you don't really get a choice of constant depending on how you set this up, right? If you're given a function like this, you notice x squared plus this squared is equal to 1. I mean, the 1 just so happens because from this function, there's a 1 here, so that's your constant. But fortunately for you, it's a constant, so you could play the implicit differentiation game and get this derivative. If it's not a function, then you can't really do it. If it's not a constant, any constant, then it doesn't really work out. So that's one situation where you can't really choose a constant. Sometimes you're given just the equation, f of x, y is equal to any constant c, then the constant doesn't matter at all. The solutions to f of x, y, z is equal to c. In a lot of conditions, you're able to find, you have one variable defined implicitly from the other two. Here, I have z implicitly defined by x and y. Then it must satisfy these equations here because on the right-hand side is a constant. So this is the same calculation as above. And in both cases, you get simplified expressions for partial z over a partial x and partial z over partial y. So in this case, f of x, y, z is equal to e to the xy z plus x squared minus y squared is equal to pi. That's your constant pi, all right? So this equation here, it relates x, y, and z, all these variables together implicitly right? They're all tied together in some weird way, such that this formula here is always equal to pi. So how do I find partial y z? In essence, so now I pretend z is dependent on x and y. So every single time I differentiate in y, when z appears, I got to use a chain rule. All right, so here's how it occurs. So partial y of e to the x, y, z plus x squared minus y squared is equal to 0, right? What I've done here is I have this relation here, right? This is always a constant. So this has to be equal to 0, right? If x, y, z obey this equation, which it has to. Now, what I've done abstractly up top here, I'm going to do concretely down here. I'm going to differentiate y on this term here. So partial y of e to the x, y, z, I first differentiate in the y variable honestly. I pretend x and z are constants. And what do I get? I get xz, e to the x, y, z, when I differentiate in y in this y variable first. But remember that z here is defined implicitly in terms of x and y. So what I have here is xy is equal to, I need to also differentiate this in terms of the dependency in y via z. So what do I get? I get a term that says xy e to the xyz, right? This is ddz of this function here. And then there's partial z, partial y, partial y of partial z. All right, so let me clarify this. This part here is given to me by partial z, partial of e to the xyz in terms of z times partial z over partial y, right? Because remember, z is defined implicitly. We're pretending z is dependent on x and y. It's implicit. We don't really know how it depends. We can't see it, but we know that it must depend on x and y because it has to satisfy this equation here. So we have to write this here. And then now we go forth. We go to the next point here. Partial y of x squared. Well, x squared is just honestly x squared. X squared doesn't depend on anything. This is 0. Minus partial y of y squared. So that's 2y must be equal to 0. So let's clean this up a bit. This says xz e to the xyz plus xy e to the xyz partial y of partial z minus 2y is equal to 0. Now at xyz is equal to 1, 1, 0. We plug this in, all right? xy, so z is equal to 0. This term vanishes. This is 0 plus xy is 1, 1, right? That's 1 times e to the 0, because z is 0. That's 1, minus 2y, y is equal to 1. So this means that partial y, partial z is equal to 2. So yes, so in this case, we're treating z as a function of y, and y is just an independent variable, and other variables are also independent variables, all right? So the trick here is whichever function, whichever variable you're taking the derivative of, so in this case, you're taking the derivative of z in y, this derivative that you're differentiating has to be treated as a function of the partial you're evaluating. In this case, z has to be treated as a derivative, as dependent on y. So that's why you get this extra term here. Let's try a different one, and we'll wrap up. Let's say b here. Let's do partial x of y at 1, 1, 1. All right, so in this case, I want partial x, once again, of e to the xyz plus x squared minus y squared, it's the same function, is equal to 0 because partial x of pi is still 0. It's a constant. In this case, I have yz e to the xyz plus something times partial x of y. What goes in front here? What goes here? Right, so it's zx, right? What I'm doing here is I now, by chain rule, I need to differentiate in y because I'm treating y as implicitly a dependent on x and z. So here I have xz e to the xyz, partial xy. And then I have plus 2x minus 0 because partial x of y squared is 0. And now at the point 1, 1, 1, you plug it in as follows, right? So you get e plus, I guess, e again, plus 2 is equal to 0. So you get partial x of y is equal to minus 2 minus e over e, right? Or if you want to simplify this, it's 1 plus 2 over e. Well, let me just point out, this simplifies things a great deal, right? I can't imagine trying to evaluate the derivative of let's say you want to do this directly, find partial x as a function of, partial x of y. Well, you have to somehow find an expression of y in terms of x and z from this expression here, which is horrible to manipulate. But implicit differentiation allows you just to look at this somewhat nice function in terms of x, y, z separately, and apply the chain rule in the correct way, and then you can read off what your derivative has to be at the relevant points. Oh shoot, did I screw? Oh yeah, you're right. Sorry, I screwed up the entire point of my example. You're right. So I lose all my marks here. Well, most of my marks here. Sorry, guys. There was a point of making this example, the second part here. Good catch. So here, partial x of y squared, you have to do, y is dependent on x and z. You're entirely right in chat. Thanks for that. This is minus 2 times y times partial x of y again equals 0. Right. Okay, so now let's plug this thing in. You now have e plus e for partial x of y plus 2 minus, well, y is 1, so this is minus 2 times partial x of y equals 0. All right, so now let's do this. Right, so let's clean this up a bit. This is e plus 2 is equal to e minus, plus e minus 2 partial x of y is equal to 0, right? I just factored out the e and minus 2. This means that partial x of y is equal to, what is this? Minus e plus 2 over e minus 2.